Okay, so here we are with lesson number 2, and today we're discussing resistance and power. We've talked about current and potential a little bit in a previous lesson, so let's turn our attention now to some different things. The amount of current that can flow in a circuit depends on two things. One of those things is resistance, and the other is potential. So if you have lots and lots and lots of batteries that are hooked up to, say, a DC circuit, you're going to have lots of current. The other thing, though, is this thing called resistance. And we need to look at what resistance is all about. Okay, so we're going to talk about some of these electrical characteristics. Really, let's look at these two diagrams of cars on a freeway. And of course, you've got one path right here, and you've got another path right here. And the main difference between this section of the highway here and this section of the highway here is that this path, this much more broad path, allows traffic to pass much more easily than the very narrow path. And so this is very, very similar to electric current. This would be very low resistance, and this would be very high resistance, because the opposition of current is called resistance. And so we can do lots of experiments where the current through a load is varied and the potential across the load is measured. And really what we could do is we could graph current versus potential. And what we end up getting if we were to do an experiment like this of potential versus current is we get a pattern that looks something like this. And this kind of phenomenon is known as Ohm's Law. And it's that in a given circuit with a given resistance, we get a pattern that's a linear relationship. And the slope of this line turns out to be something very interesting. So if we start with y equals mx, and we basically say, okay, well, y really is the potential, and x is really the current. This slope right here turns out to be the resistance of the circuit, which represents the opposition to the flow of current. Okay, this gives us a law that we can write as V equals Ri, or V equals IR, depending on how we want to express it, and this is known as Ohm's Law. Okay, so this is the equation, of course, written in a little bit of a different way, but really, no matter how you write it, it's all Ohm's Law. Here, though, it kind of points out that the units of resistance are volts per amp. But again, like voltage itself and like current itself, these are both derived units. The unit of resistance carries a derived unit of ohms, and the symbol that we use is the capital letter omega. And V is, of course, potential difference across a resistor, and I is the current in amps through that resistor. And so this is the relationship that we get. So let's take a look at a quick example. An electric stove element is connected to a 240 volt supply and has a known resistance of 19.8 ohms. What current does this element draw? All right. Well, we know V, we know R, we know the resistance, and we'd like to be able to determine the current through this element. So we use V equals IR, and we can rearrange it to solve for the current. And when we make our substitution, we end up with 12.1 amps of current through this stove element, which is actually a lot of current. Moving along, what's the resistance of a 1200 watt hair dryer that draws 10 amps from a 120 volt circuit? Okay, so really anything that you plug into the wall, if you know the current that it draws, and if you know the potential, and most of the time in North America, we have 120 volts that is supplied by our sockets in the wall. We have 120, we have 10 amps. We can certainly discover the resistance of this. We've got about 12 ohms would be the resistance of this hairdryer. There's a few things that affect the resistance of wires, okay? And one of those factors is length. If you have a wire that's long, you will have much more resistance, Okay, and this is one of the reasons why very often they tell you don't take extension cords and connect them end over end over end over end so that you have this huge, huge, huge long wire, because you change the resistance. And because you change the resistance in that, then you can affect other parts of whatever it's connected to. Here we have, in general, just a proportion, and we've got the initial resistance over the second resistance, the changed resistance, the final resistance, is equal to L1 over L2, right? So this is proportional, linearly proportional. So if you get longer wire, you get more resistance. Cross-sectional area, if this one's inversely proportional. If you have a larger cross-sectional area, you will have less resistance. So this is as the area of the wire, as the cross-sectional area of the wire gets larger and larger and larger, of course you get less resistance because the current can pass through easier. So this is inversely proportional. R1 over R2 is equal to A2 over A1. We'll kind of keep on going with this. The material, you know that of course most wires in the home used to be made from copper, right? Copper wire throughout the house. Copper is very expensive these days, so they're looking, and they use other materials as well. But in general, this thing called resistivity is a measure of how much resistance a given material has. And so the resistivity is linearly proportional to the resistance. So if you have a material that has more resistivity, it will have more resistance. So we look for low resistivity materials. So we get R1 over R2 is equal to ρ1 over ρ2. This is a symbol for resistivity. And temperature, in general, as temperature increases, so does resistance. And we're not going to introduce an equation for this because we don't need to worry about it. But as temperature goes down, very often materials will become conductive. And there's a lot of physics that's involved in this little sentence right here. That's involved in the temperature dependence on resistance. And so at low temperatures, resistance is very, very, very low. And there's a lot of physics in this, and a lot of very interesting physics. It's one of the reasons why low temperature physics is a very blossoming field. Here's an example to kind of put some of those pieces together. A 200 meter piece of aluminum wire has a resistance of 1.7 ohms. What is the resistance of a 50 meter piece that's cut from this 200 meter piece? Well, I know the initial resistance of the 200 meter piece, right? I'd like to find out the resistance of a 50 meter piece. And if we look at the proportion that we're given, R1 over R2 is equal to L1 over L2, and we rearrange and make a substitution, we come up with our new resistance as being 0.425 ohms. Okay, so that's the new resistance. Let's continue on with this. Let's say we're now going to change the cross-sectional area of a 50 meter piece of aluminum wire. Basically, how would that cross-sectional area have to be changed to give it the same resistance as the 200 meter piece of wire in the example above? Okay, so basically what we have now is we've got R1 is 1.7 ohms, the initial resistance that we had before. R2 is 0.425 ohms. So we want to adjust the cross-sectional area of this, and we want to see, okay, what would we need to do? Well, A2 over A1 is equal to R1 over R2, and this is a factor of 4, or a difference of 4. And so what this means is that we would need to increase the cross-sectional area by a factor of 4 in order to get the same kind of resistances that we had in the first. Okay, so the area would need to be quadrupled. Let's talk very briefly about power in electric circuits. Power is, of course, the rate at which work is done, work over time, which can also be considered energy over time. And in an electric circuit, we talked yesterday, or last lesson, about energy being voltage times current times time. So the energy that's used in an electric circuit is equal to these things. Well, we can simplify then for power, and we notice that power is equal to voltage times current. And this is our formula for power in an electric circuit. So again, let's take a look at a few examples, and these are all very, very straightforward. What's the maximum power that can be drawn from a standard 120 volt household circuit that has a circuit breaker of 15 amps? So our household circuits are usually rated at about 120 volts, except for the oven and maybe even the dryer. A lot of the circuits are rated at 15 amps. Some of them are at 10 amps in the home. But let's say we want to know the maximum power that we can get from 120 volts at 15 amps. Well, this is, of course, very straightforward. Power equals voltage times current. And we get about 1,800 watts. So if we have a power rating on some object, say a hairdryer or something that takes a lot of power, this would be the maximum power allowable for that object. Okay. Let's take a look, though, at another example. Here we have, what's the power rating of a stereo amplifier if it's plugged into a 120 volt outlet and has a resistance of 120 ohms? So here we're being asked to calculate power, but we're not given current. And so we know that power is equal to voltage times current, but perhaps we can use this resistance to find out. Resistance, current really, if we don't have it, is equal to voltage over resistance. So we can make a substitution here into our formula for power, and we come up with another form of the power formula, and that's V squared over R. So we can use this if we're given these two things, and we can say very, very simply that power equals V squared over R, which is 120 squared over 120, and this simplifies out, and we get 120 watts. In very much the same way, perhaps we're asked to calculate power, and we're given resistance, and we're given current, we're not given voltage. Well, we know that power equals voltage times current, and we know that voltage equals IR, and we can make a substitution, and we get a third form of our power formula, which is power equals I squared R, all coming from the same spot. We can say I is equal to 10 amps and R is equal to 15 ohms, and we can put this together, and we get 1,500 watts, and that is the power in this circuit.